So we're going to round off the section on arc length by talking about the arc length function. So the arc length function is a function about a function, which sounds confusing, but I promise it makes sense. And we're going to relate it to the rates of change that we know and are familiar with. Our motivating idea here is that we know that we're given some function that represents a curve, and let's say we're going to start from a point a comma f of a. So that's going to be our starting point. Now, when we talk about a function as a function of x, right, we're talking about its location along the x-axis, right? But even if we're not talking about the x-axis, maybe we can talk about its location along the curve. So for instance, instead of talking about, say, some value t, we're going to talk about its location as how far along the curve from the initial point we are. And this is actually really useful construction, and it comes up a lot in when you talk about calculus variations and in classical mechanics. But what we're going to do here is we're going to develop this secondary function, which we call the arc length function. So basically, given some point t, which is at least a, the arc length function, some x, I should say. The arc length function s of x is equal to the integral from a to x of, and here I'm going to use a dummy variable t, so not the t that I was using earlier, it's x, sorry. The integral of the square root of 1 plus f of prime of t squared dt. So the t here is a dummy variable. Really the variable that matters here is the x. So this is an integral defined function where for any given x along this axis, we're going to find s. One really cool thing about this is because this is an integral defined function of something that's integrable, we hope, by continuity, this means s is which not just continuous, but a continuously differentiable transformation of x. This statement right here is so incredibly important, and if you go on to take further math, we have another special name for this, and we're going to actually revisit this in the later section of this class where we talk about parameterization. What we're saying is we can express this curve as a function of s as well, and we'll get there in a second. So first of all, let's talk about what s of x is. So it's the arc length from the point A to the point x comma f of x, right? One other really cool thing about this is that we know immediately what ds with respect to dx is. So the derivative of s with respect to x is literally the integrand. So 1 plus df over, dy over dx. So the derivative of y with respect to x squared. Which means if you write it as ds of x, dx squared, you get 1 plus dy dx squared. Aha! We get a really cool relationship here, especially if we think about the differential. So remember, the differential is, it basically looks the same, right? It basically means ds equals the derivative times dx. the differential in dx. And so really what this is saying is, so two really cool things. One, the differentials are related by ds squared equals dx squared plus dy squared, okay? Which is really cool. That's basically saying that the approximation when we turn, so we have some curve like this, right? And we approximate it using this hypotenuse, right? The hypotenuse is your delta s, and your delta y here, and your delta x here. And in the limit, so in relating the differentials, we're saying that in the limit, the differentials they satisfy this relationship as well. So super cool. And also importantly, I meant to use black here, and we can write L, the arc length, is really the integral from a to b of ds. So by reparametrizing the function in terms of s, we are now taking the integral for arc length as literally just the integral of this infinitesimal. And so let's find the arc length function for, let's just play with an example here. So we're going to find example. Find the arc length function for, what's a good curve that we want to use? We're going to use y equals sine inverse of x plus square root of 1 minus x squared with starting point 0, 1. Okay, so our a here is 0, our f of a is 1, and this is our function here that we want to find. So in order to find the arc length function, what we're actually going to do is we're going to take, if y, we can derive that to find dy dx, which is just the derivative of this, right? So derivative of sine inverse, which is 1 over square root of 1 minus x squared, plus the derivative of the square root of 1 minus x squared, which is actually minus 1 half, minus 1 over 2 square root of 1 minus x squared, which means this just ends up being 1 over 2, is that right? Square root of 1 minus x squared. Yeah, that should be right. You can double check if you'd like, but yeah, that should be right. Okay, so that's the derivative of y with respect to x, which means then that s of x, so this continuous transformation of x into our new parameterization in terms of, so s, in fact, I'm going to drop the of x at some point. I'm just going to write s is this with respect to x. So is the integral from 0 to x of the square root of 1 plus 1 over 2 square root of 1 minus x squared squared dx. Actually, I'm going to use a different letter here, right? Because we don't want to get confused. We're going to write dt. So t squared, and then dt here. So if you square that, right, we're going to get 1 plus 1 over 4, 1 minus t squared underneath the square root dt. Okay. And then we can combine things here so that we can write this as a single expression. So remember, s literally equals from the integral from 0 to x of square root of, and I'm going to combine this. So I'm going to multiply 1 by 4, 1 minus t squared over 4 minus 1 over t squared. So minus t squared, 4, 1 minus t squared, minus 1 over 4, 1 minus t squared, dt. Okay. Then we get 4 minus 4t squared minus 1 over 4, 1 minus t squared, all underneath the square root. And then you get 3 minus 4t squared over 4 times 1 minus t squared squared. Okay. Then, what can we do from here? Well, let's see. So let's just double check that everything went well here. Oh, that's a plus. Sorry. Plus. So that should be a 5. Not that it matters too much. 5 minus 4t squared. And so we're going to pull out the 1 minus t. No, that does not help. What can we do here? So we get 5 minus 4t squared over 4 minus 4t squared. That's in our integrand. So it almost feels like it should have been easier to write this as yeah. So if we were to perform the long division again, yeah, we wouldn't have gotten anything nicer here, because we should get the same expression here if we go from here to performing the long division. We would get the exact same thing that we started with. That said, maybe we can pull out the 4 from the denominator as a 1/2. So equals 1/2 the integral from 0 to x of the square root of 1 minus t squared over 5 minus 4t squared dt. Okay, so let's try a substitution here. So we're going to let u equal 1 minus t squared, okay, which means t squared equals u, 1 minus u, I should say, sorry. 1 minus u, and du equals 2t dt. But that's not super helpful either. So maybe if we do t equals the square root of 1 minus u, then we can find dt in terms of du this way. So that would be minus 1 over, no, positive 1 over 2 square root of 1 minus u du. And 1 minus u that's obviously 1 over 2t. It's the same thing. Does it matter? Okay, well, let's see if we can figure anything else out with this thing. So that means the integrand becomes 5 minus 4 times 1 minus u over u. And then the dt is 1 over 2 square root of 1 minus u du. Okay. Does that give us anything? And then 0 and x have to be transformed as well. So remember that u of 0 is 1, and then u of x is going to be 1 minus x squared. So we end up with 1 to 1 minus x squared, 1/2 in front. Okay, let's see if we can clean this up. So the numerator here, I'm going to split this up in two. Square root of 5 minus 4 plus 4u. All over square root of u times 1 over 2 square root of 1 minus u du. Is this going to help us? Maybe. And then, of course, this is the integral from 1 to 1 minus x squared. Half of that. Okay, then in the numerator, we get 1 plus 4u square rooted, square root of u, times 1 over 2, square root of 1 minus u du. Go from 1 to 1 minus x squared, 1/2 in front. All right. Not quite there yet. But maybe if we combine some more things. So for instance, u to the 1/2 times 2 times 1 minus u to the 1/2. That means you can combine underneath the square root. So if I'm going to pull out another 1/2, that's just scratch work. So I was just going to say, I can combine underneath the square root to make a square root of u minus 1 over u. Sorry, u times 1 minus u. And then the numerator is going to be the square root of 1 plus 4u. Okay, then I get 1/2 times 1/2 is 1/4 by pulling out the 1/2 inside the integrand. I get 1 to 1 minus x squared of the square root of 1 plus 4u over u minus u squared du. And that's not any better, is it? Slightly, but not really. Well, we could come back to that later, but that's where we're at. And this, in theory, if we could find this integral, would be the arc length function for this curve. So in the next section, we apply the arc length construction to something that feels very similar to what we've done before, which is we explored the volume of a solid of revolution, and now we're going to talk about the surface of revolution and how to find the surface area of such a construction. It's very similar to